Have you ever wondered what a construction site would look like with no foreman? No one shouting out orders, just a team of robots working together perfectly to build something complex. Well, it might sound like science fiction, but it's closer than you think. Today, we're going to dive deep into a really elegant solution from a groundbreaking research paper all about decentralized construction. So this is the big question, right? Nature figured this out ages ago. You look at termite mounds, these incredible complex structures, and there's no single termite in charge. So how do they do it? And more importantly for us, can we crack that code and teach our robots to do the same thing? All right, so if you're trying to solve a puzzle this massive, where do you even begin? Well, the researchers did something pretty smart. They looked to the planet's original master builders for a little inspiration. Yeah, whether you're talking about beavers building dams or ants constructing these massive colonies, there's a secret sauce they all share: decentralized control. There's no big boss calling the shots. Instead, every single little creature is just following a few simple local rules. Things like, if you see a hole here, put a piece of dirt there. And when you have thousands of them all following these basic rules, this incredibly complex, intelligent structure just emerges. It's amazing. Okay, so how do you take that beautiful, kind of chaotic system from nature and turn it into a predictable, reliable, robotic workforce? Well, it all starts by laying down some ground rules and figuring out exactly what our little construction bots can and can't do. So each robot in this system is actually really simple. It only has 3 basic moves. It can pick up a brick, it can move 1 square over, and it can put the brick down. That's it. That's the whole list. The real genius here isn't what they can do, but the really clever rules about what they can't do. You see, these aren't some kind of superbots from a movie. They have real-world physical limits. They can't just climb up a wall. Anything steeper than a single brick is a no-go. And to place a brick, they have to be standing right next to the spot at the exact same height. Plus, as we're about to see, some moves are just flat-out forbidden because they're way too tricky to pull off reliably. And here is a perfect example of one of those forbidden moves. Just think about it, trying to perfectly slot a brick into a tiny 1-block-wide gap. For a robot's sensors and little arms, that's a total nightmare. The chance of getting it wrong, of jamming it, is just too high. So to guarantee success, the system just says, nope, we're not even going to try that. And that brings us right to the heart of the problem, the million-dollar question. You have a whole swarm of these robots, each following these simple rules. How on earth do you make sure they actually finish the job? How do you stop them from, literally building themselves into a corner or blocking a teammate from making the winning move? The paper's answer to this coordination nightmare is just so elegant. They decided to forget about having one central commander. Instead, you push all the intelligence out to the edges. You give every single robot its own identical, pre-calculated rulebook that guides every single move it makes. Now, this smart rulebook is called a supervisor. You can think of it like a really advanced GPS that lives inside each robot. It's constantly looking around and asking, okay, where am I? What does the building look like right now? And based on that, it gives the robot a menu of pre-approved, totally safe moves. The robot can pick any move from that menu, and it knows for a fact that none of them will mess things up. And here's where it gets really, really cool. This isn't a system that has to learn as it goes through trial and error. The supervisor is what we call correct by construction. That means using some pretty heavy-duty math, the system is proven to work before a single robot even powers on. It's like you've already solved a maze and highlighted every single correct path before anyone even takes a first step. So how in the world do you actually write this foolproof rulebook? Well, the technique is called modular synthesis, and it's a really clever process of combining 2 critical digital blueprints. You basically need 2 key ingredients. First, you need a model of the goal, and not just the finished building, but a complete map of every single possible intermediate step to get there. Second, you need a model of the player, a perfect digital owner's manual for a single robot, detailing everything it can and cannot do. The synthesis process then basically smashes these 2 models together using a field of math called supervisory control theory. Think of it like the ultimate simulator. It takes what the robot can do and plays it out against every possible stage of construction. And it just preemptively identifies and cuts off any sequence of moves that could possibly lead to a dead end. So the final rulebook that pops out of this whole process comes with 3 rock-solid mathematical guarantees. First, co-accessibility. You'll never get stuck. There is always a path forward. Second, task observer. Robots won't get in each other's way. They can always get to work or move aside for a teammate. And third, total reciprocity. The system avoids deadlocks where two robots are just waiting on each other forever.
Okay, I know this all might seem a little abstract, so let's look at a concrete example from the paper to see how this system prevents a total disaster. So, let's picture this. We've got a green robot, and it's working inside this little U-shaped structure. Meanwhile, a red robot is on the outside, and it's getting ready to place the next brick.
And here it is, the critical moment. What happens if the red robot just places its brick right there and closes the U? The green robot is now trapped. Remember that one brick high climbing limit? It's stuck. The whole project would just grind to a halt. Game over. But this is exactly where the supervisor shines. The supervisor software on board the red robot sees the state of the world. It knows where the green robot is. It looks one step ahead, sees that placing the brick would create a trap, a dead end, and it simply removes that action from the red robot's menu of options. The red robot is literally forbidden from making that catastrophic mistake. Now, there's a formal name for this ironclad guarantee. It's called non-blocking. And all that fancy term means is that the task can always be completed. It's the mathematical proof that no matter what valid choices the robots make, there is always a way to get to the finished structure. They can never, ever get permanently stuck. So let's zoom out for a second. What's the big picture here? Why does a system of robots that is guaranteed to succeed, why does that matter so much? Well, the implications for the future of construction are, frankly, enormous. What this research really gives us is a complete toolkit. It provides a formal language to define the problem, a method to generate a guaranteed solution, and a final controller that's totally decentralized and scalable. And the beauty of it is you design the supervisor once, and then you can just copy and paste it onto 10 robots, 100, 1,000, and that guarantee of success holds for all of them. Just think about the applications here. Imagine a swarm of simple, cheap robots being deployed after an earthquake or a flood. They could quickly assemble emergency shelters or containment walls, all without needing a complicated central command system. They could just react to the environment and work together to get the job done. Guaranteed. You know, this research really marks a fundamental shift in thinking, from designing robot swarms and just hoping they'll succeed, to designing systems that are mathematically proven to succeed from the start. So the question I want to leave you with is this. If we can take failure completely off the table, what challenges that we once thought were impossible might we finally be able to build? On the moon? Deep underwater? The future of construction just got a whole lot more predictable.